In the previous lecture, we talked about the equation, which is the Ergun equation, which can be used to calculate the pressure dropped in back bed for laminar, transitional, and turbulent flow. And this was the objective of whatever we have done till now. In this lecture, lecture number 6, I want to talk about an example to show you how we can apply using the Ergun equation. Let me go through the problem with you, read it, sketch it, and then we'll see how to solve it. A gas absorption tower of diameter 2 meters contains ceramic rashing rings randomly packed to a height of 5 meters. What's this? So I have something like that. So this is a gas absorption tower. The diameter, so this thing from here to there, this diameter, so I will just call it big D, is equal to 2 meters, contains ceramic crashing rings randomly packed to a height of 5 meters. So usually, for example, we have a mesh like this to support the backings, and those are called, so they are made of ceramic, they're called rashing rings. And if you remember, I showed you the rashing rings. Those are the rashing rings. Those are the ceramic rashing rings. So the back bed is full of those ceramic rashing rings. Why? We are putting them to increase the surface area of contact between the solid and the fluid. So those rashing rings are packed everywhere here. Okay. And the height from, so this is the height or the length of the back bed, I will just call it L, is equal to 5 meters. Air containing a small proportion of sulfur dioxide passes upwards through the absorption tower. So I am passing air here. So air is going through the rashing rings. Hopefully we are getting rid of the sulfur dioxide. So you want to get rid of sulfur dioxide, it's O2. It's a harmful gas. Passes upwards through the absorption tower at a flow rate of 6 meter cube per second. So the flow is going from here to there, and hopefully those, let us say, packings are absorbing, they are just taking this SO2, and hopefully the air going up here is clear or clean. So what is the volumetric flow rate? I will just write it here. V dot is equal to 6 meter cube per second. The viscosity and density of the gas may be taken as 1.8 times 10 to the minus 5 Pascal second. So this is what? This is the viscosity of the gas. Okay, 1.8 times 10 to the minus 5 Pascal second. And the density of the gas is equal 1.2 kilogram per meter cube. At least you shouldn't be surprised when you see this value. This is close to the density of air, if you remember from chapter 2, and this is mainly air with little bit of sulfur dioxide. Now he's giving us more data. Surface area per unit volume of the backed bed is 190 meters square per meter cube. Okay, and also he's saying that, so this is the details of the backing, and also he's saying voidage of randomly packed bed is 0.71. Voidage, what is this? Voidage and surface area per unit volume. So the surface area per unit volume of the packed bed, please open your eyes here. This is not the surface area per unit volume of a particle. This is not A sub nu. No, this is A, which is the surface area per unit volume of the whole packed bed. And the voidage of randomly packed bed, what's this, the voidage? Voidage is the void fraction, which is epsilon. So in addition to those details here, he is telling you that A is equal to 190 meters square per meter cube, and also he is telling you that epsilon is equal to 0.71. So this is all the information in the problem. Now what is required? calculate the diameter of a sphere with the same surface volume ratio as the rashing rings. So now I have the rashing rings, but I want the equivalent diameter, which is d sub p. Okay, d sub p. This is the first thing, and the second thing, calculate the pressure drop across the packing in the tower, and also he's asking for delta p inside the tower. So how to solve this problem? First of all, we want to find dp. So based on the given data, let us go to the next slide. So those are the rashing rings. So you know that this is what we have, which is this is A and this is epsilon. And I want to remind you of this equation, which is the equation of A. So now A is given to you, which is equal to 190. Epsilon is given to you, which is 0.71. And this is your unknown, which is dP. So please solve. So solve for dP, and you should get something close to 9 millimeters. Okay, not exactly. So you will get something close to 9 millimeters, which means that those are small rashing rings, almost one centimeter long. So this is straightforward, this is easy, and we have just calculated the diameter of a sphere with the same surface volume ratio. The second thing that he's asking for, delta P. So which equation to use? We're going to use Ergun equation, calculate the pressure drop. So we can use Ergun equation, and also I will keep this for you to calculate. But let me first look at the equation. But you can use this equation, or you can use the other form, which is the non-dimensional form of it. So what do we have? Do we have everything here? So delta P is equal to 150. This is a constant. Viscosity is given to us. The length is given to us. Epsilon is given to us. Delta P, we just calculated it. Density is given. dP given. Length is given. Epsilon and epsilon. So the only thing that we have to worry about is V prime. So what is V prime? We said V prime is the superficial velocity, which is the velocity based on the empty bed. Okay, so this is the same as we have done before. It is like the velocity inside a pipe. And how did we calculate velocity inside the pipe? So it's just simply V dot divided by the area. Did he give us those data? I believe yes. Oh, sorry, I have to go this way. So V dot was given to us, which is this 6 meters cubed per second, and the diameter of the bed is given to us as 2 meters. So what do we have to do then? I can go here and say V dot is equal to 6 meters cubed per second. And what is A? So A is equal to pi d, or let us just keep it the big D, pi d squared over 4. And you know that D is equal to 2 meters. So you get the A, the area, you put it here, and this will give you V prime. And once you get V prime, you just substitute it in this equation here and there, and you can get delta P, as simple as that. So this was a direct application of, let us say, of the Ergun equation to find the pressure drop. And also we used the equation for the packed bed for specific, let us say, surface area to find the diameter. In the next lecture, I'm going to talk about another example.